This screencast is going to go over the basics for orbital diagrams and connecting our electron configurations to these different types, basically of a pictorial representation of what's going on with individual atoms and individual electrons in an atom. So sometimes these are called box diagrams. There's several different varieties if you look in different textbooks, if you look online at different resources. But typically what we do is we will use a box to show the potential location for electrons. So what we did in class already was we wrote what are called ground state electron configurations. So we used our colored periodic table. We colored in the S, these first two columns, the P with these 6 groups over here, the D, and then the F, and then we practiced writing electron configurations. So that's great, but it's not really as visual as what you're going to find in an orbital diagram. So if we talk about a ground state configuration, we just mean that electrons are in their lowest allowable energy level. So their lowest allowable energy level. I kind of call that the electrons being home. And then of course you know from the flame test lab, electrons can get excited. When they get excited, they jump up in energy. They have to absorb energy to jump up. And then when those electrons return to ground state, they will emit that energy as different wavelengths of light. So that's why we saw those different colors when we did the flame test lab. So when we do these, we're assuming that all the electrons are in their lowest allowable energy level or ground state. So every single time we draw a box, the capacity for each box is 2 electrons. So if you draw them as little arrows going up and down, it actually takes a while, especially when you think about how many electrons we're going to have to draw, to do both sides of the arrow. So an alternative is to just do kind of half arrows. So you show that one spinning up and this one spinning down. We'll talk in a minute about why is one going up and one going down. Alright, so I've given the principal quantum numbers. You guys aren't responsible for knowing principal quantum numbers, but they do correspond to the S, P, D, and F that we saw with our electron configurations. So with the S, if you go back to this periodic table, every time we looked at S, there was always, the capacity was 2 electrons. It always went 1, 2, 1, 2, 1, 2. Well, if a single orbital, which is what these boxes are going to be, can hold 2 electrons, then we would only need 1 box for an S. If we think about P, that was always 1 through 6, 1 through 6, 1 through 6. And if each box or orbital can hold 2 electrons, then we'd only need 3 boxes. For our D, since it can hold 10, we would need 5 boxes or 5 orbitals. And for F, since it has a capacity for 14, we would need 7 orbitals. So that's how we know how many boxes are we supposed to draw for each individual sublevel. Alright, so you'll see this first one for nitrogen. If we write out nitrogen's electron configuration, it's 1s squared, 2s squared, 2p to the 3rd. So if we check that, we add up 2, 2, and 3, we get 7. And nitrogen's atomic number is 7, so we've accounted for all 7 electrons. So what they've done is they've kind of taken this notion of this probability of finding electrons and kind of drawing it as a picture. And so 1s has the 1 box and it's full with its 2 electrons. 2s has 1 box and it's also full with its 2 electrons. And then notice what's happening with P. There's 3 spots for electrons, but notice they're all occupying the empty ones before they pair up. We'll talk about why that is, but if you think about it kind of in common terms, if I were to place 3 chairs up at the front of the classroom and then pick 3 people to come sit in those chairs, most likely, unless there was something strange happening, each person would choose to sit individually in their own chair. And then if I said, all right, 3 more people need to come up and sit in these same chairs, their only option would be to double up and sit in the lap of somebody that was already seated in a chair. So we know electrons are negatively charged, and if they have the opportunity to get away from one another, they will, because like charges repel. So that is why they're going to occupy the empty orbitals first before they pair up. And so you will want to place single, single, and then let's say we were going to do oxygen, which has 1 more electron, then that electron would then be forced to pair up. All right, so looking at the picture, the capacity for each orbital, the max is 2 electrons, so each one can hold 2. And why are the electrons in the 2p orbitals arranged like they are? Well, the answer is electrons repel one another, and so they will not pair up until they are forced to do so. So we have 2 principles that kind of go along with these orbital diagrams, and I will tell you that these are commonly switched and missed on the unit test, so try to come up with some sort of mnemonic or memory clue to help you keep them straight. So the Pauli exclusion principle states that the capacity of each electron orbital is 2 electrons. So that's the first part of the Pauli exclusion principle. And those electrons must have what's called opposite spin. That gets into a lot of quantum mechanics and physics. That's kind of beyond what we study. But if you think about it this way, if you have 2 electrons in the same space, one would be rotating kind of into that phase and one would be rotating out. And that keeps those 2 electrons able to stay in the same space. So that's the Pauli exclusion principle. The capacity is 2 and they have to be spinning in opposite directions. All right, Hund's rule is the one that says, why do these electrons go single, single, single rather than pairing up? So what this one says is electrons will occupy empty orbitals within the same sublevel before pairing up. Electrons will occupy empty orbitals within the same sublevel before pairing up. So again, if we were going to do oxygen with one more electron, that electron would be placed right there. All right, so again, I hope you're getting kind of the sense of these are really just taking our electron configurations and turning them into pictures so it's easier to see. And we'll start talking about ion formation and where do electrons go when they're gained or lost. And these really help you kind of visualize where those are going to go. At first, they may be a little challenging, but they really do give you nice representations of what's happening. So we're going to do the configuration for sulfur. So we start up 1s squared, 2s squared, 2p6, 3s squared, and then 3p4. And it's really easiest, up here when you look at this, you see that each of them are labeled. And textbooks, like I said, will do this a different way. Sometimes they'll draw, little things like that to show you. What I recommend you do is to write out the configuration and then just draw your boxes in. So 1s, anytime you have an s, is going to have 1 orbital. A 2s, going to have 1 orbital. A 2p is going to have 3 boxes to hold those 6 electrons. The 3s is going to have 1 orbital to hold 2 electrons. And then a 3p is going to have 3 orbitals. This one's not going to be full. It's only going to have the 4 electrons in it. So it's pretty much, you don't even really have to think a whole lot about it. You're going to fill all these up. I do like to place them single, single, single. Just helps me remember that you don't pair them up when you're not supposed to. So the 3p4, we're not going to have 2 pairs. They're going to go single, 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 and then that one will be forced to pair up. Now, these electrons, guys, are not stationary. They're not staying in one place. So for us to say, oh, that electron is definitely in that orbital, is a little kind of over the top. But it's really just a representation. So if you wanted to put that, 4th electron in that box or that box, it would be totally fine. Just make sure that you do have the opposite spin on whichever one you pair up. All right, so the next one's asking for MO, the complete and the noble gas configuration. And then we're going to draw the orbital diagram. We're going to do what's called the abbreviated orbital diagram. Because as you can see, it gets very repetitive, just like our electron configurations did. And so the noble gas we'll do it the same way with the shorthand notation. So for MO, our configuration is 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s2, 3d10, 4p6, 5s squared, and 4d4. Our noble gas configuration, which would take care of everything up to there, we would put Kr in brackets as the last noble gas, and then 5s squared, 4d, 2d4. So if we're going to draw the abbreviated, we would draw one box for that 5s, and it's full. And then for the 4d, remember that that D block holds 10, and so if each box can hold 2, then we need 5 boxes. So a common question is, do we really need that last box? And the answer is yes, you do need to draw the empty box, because again, this shows a potential for a place to come bond or for electrons to be lost. So that would be the abbreviated orbital diagram for molybdenum. Alright, so back here you've got additional practice. So number of electrons, of course, comes from the atomic number. You're doing the orbital diagram and the longhand electron, so that's called the complete or the longhand. And then down here you get a little bit of a break because you are allowed to do the noble gas electron configuration along with the abbreviated orbital diagram. So again, just making sure you're checking those total electron counts before you draw on your orbital diagram. So take care of that practice and we will check them together.